26.4 Resistance and Temperature. In this video, we will cover the outline for our discussion on resistance and temperature. First, we will explore the temperature dependence of resistivity and define the temperature coefficient of resistivity. Next, we will look at resistance variation specifically in metals. Following that, we will provide a brief introduction to semiconductors. Finally, we will discuss superconductors and the concept of critical temperature. Over a limited temperature range, the resistivity of a conductor varies approximately linearly with temperature. The relationship is given by an equation where the resistivity at a given temperature equals the reference resistivity multiplied by the quantity 1 plus the temperature coefficient times the change in temperature. In this relationship, the first term represents the resistivity at a specific temperature in degrees Celsius. The reference resistivity is measured at a reference temperature, which is usually taken to be 20 degrees Celsius. The multiplier for the temperature difference is known as the temperature coefficient of resistivity. The temperature coefficient of resistivity can be expressed mathematically. It is defined as the fractional change in resistivity, which is the change in resistivity divided by the reference resistivity, all divided by the temperature interval. The change in resistivity is simply the final resistivity minus the initial reference resistivity. The temperature interval is the final temperature minus the reference temperature. The unit for this coefficient is inverse degrees Celsius. Because of this predictable relationship, this property is incredibly useful for making precise temperature measurements by carefully monitoring the resistance of a material. Because electrical resistance is directly proportional to resistivity, the variation of resistance for a sample follows a very similar linear relationship. We can state that the final resistance equals the reference resistance multiplied by the quantity 1 plus the temperature coefficient times the change in temperature. In this case, the reference resistance is measured at the reference temperature. For many metals, such as copper, the resistivity is nearly proportional to the temperature over a quite wide range. However, it is important to note that a nonlinear region exists at very low temperatures near absolute zero. As shown in the graph, the resistivity in metals generally increases as the temperature increases. At high temperatures, this resistivity is primarily dominated by collisions between the moving electrons and the metal atoms. But as the temperature approaches absolute zero, the resistivity does not drop to zero. Instead, it reaches a finite value known as the residual resistivity. This residual resistivity near absolute zero is caused mainly by the electrons colliding with impurities and structural imperfections within the metal lattice. Moving on to another class of materials, some substances actually exhibit negative values for their temperature coefficient of resistivity. For these unique materials, the resistivity actually decreases as the temperature increases. We call this class of materials semiconductors. This unique behavior occurs because as the material is heated, there is a significant increase in the density of charge carriers available to conduct electricity, which more than offsets the increased scattering from atomic vibrations. Superconductors represent a fascinating class of metals and compounds. For these materials, the electrical resistance drops completely to zero when they are cooled below a certain specific temperature. This specific threshold is known as the critical temperature. When heated above this critical temperature, the material behaves just like any normal metal. Superconductivity was first discovered in the year 1911 by Heike Kamerlingh Onnes while he was studying mercury, which has a critical temperature of 4.15 Kelvin. Below this critical temperature, the measured resistivity is incredibly small, less than 4 times 10 to the negative 25 ohm meters, which is effectively zero for all practical purposes. This graph displays the electrical resistance versus temperature for a sample of mercury. You can clearly see that as the temperature is lowered, the resistance drops discontinuously to absolute zero right at the critical temperature. For mercury, this critical temperature is 4.15 Kelvin. Because the resistance is completely zero below this point, persistent electrical currents can be established in superconducting loops. These continuous currents can flow without any applied voltage and without any measurable decay for several years. When studying modern superconductors, we find that the critical temperature is highly sensitive to the material's chemical composition, the applied pressure, and its molecular structure. There are two main types of superconductors. The first type includes traditional metals like mercury and lead, while the second type consists of ceramics, which are known as high critical temperature superconductors. Examples of these high critical temperature materials can reach critical temperatures of 92 Kelvin or even 134 Kelvin. Interestingly, excellent room temperature conductors like copper, silver, and gold do not exhibit superconductivity at all. A major practical application of this technology is the creation of superconducting magnets, which can produce magnetic fields approximately 10 times stronger than the best normal magnets. Let us summarize what we have covered in this section. We learned that the resistivity in metals generally increases in a linear fashion with temperature, following the mathematical relationship we explored earlier. We also discussed semiconductors, which have negative temperature coefficients, meaning their resistivity drops as the temperature rises. Next, we explored superconductors, a special class of materials that exhibit zero electrical resistance when they are cooled below their specific critical temperature. Finally, we noted that for normal metals, the residual resistivity observed near absolute zero is caused by electrons colliding with impurities and structural defects. To conclude, here are some review questions for you to consider. First, think about why the resistivity of a normal metal reaches a non-zero residual value as the temperature approaches absolute zero. Second, based on the definition of the temperature coefficient, consider why the resistivity of a semiconductor decreases with temperature, while the resistivity of a typical metal increases with temperature. Reviewing these concepts will help solidify your understanding of how temperature fundamentally affects electrical resistance.